Good morning, good afternoon, and good evening, everyone. Welcome to today's session, which focuses on a Python tutorial demonstration showing how to access and use data from the Copernicus Marine Service. My name is Marine Delorme. I'm a Training and Capacity Development Officer at Mercator Ocean, and I will be your host for today's webinar. The goal of this notebook is to guide you step by step through the analysis of sea surface temperature variability and climate-driven changes in the Black Sea. We will begin with basic data handling and progressively move toward more advanced diagnostics of marine heat waves, providing a practical and reproducible workflow for exploring climate signals in regional sea surface temperature datasets. With that, let's get started. Before we begin, let's quickly go over some house rules to make sure you enjoy this session to the fullest. Please don't use the chat box on your right-hand side for questions. It's there for greetings and for sharing links with you throughout the session. If you have a technical or content-related question, we invite you to use the dedicated Q&A section. Today, we will run a Jupyter notebook on a platform called BinderHub. This hands-on format directly responds to feedback we received during previous events where many of you asked for more practical hands-on session. So we hope this approach meets your expectations and allows you to actively follow along. Each participant has access to the platform and can run the notebook at the same time as the demonstrator. We strongly encourage you to do so, as we will deliberately pause during the session to give you time to complete the exercises. There will be a total of 5 exercises, and we will answer questions each time we pause. We recommend that you click on the BinderHub link now, as it may take a few minutes for the environment to launch. You can find the link in the chat on the event platform. It's being posted right now by going to the Python tutorial tab of this website and clicking on Access BinderHub, as you can see on the screen. Or you can also go to the email you received 30 minutes ago, which also had the link to the platform. If you prefer, you can also run the notebook on your own computer. However, we recommend using BinderHub as all the required packages are already installed, making it easier to follow along. Just one advice, make sure to keep your BinderHub window open throughout the session, as reopening it later may be difficult due to server limitations. As I mentioned earlier, we will answer questions each time we pause for an exercise. You can submit your questions at any time using the Q&A button at the top of your screen. Simply click on it to open the dedicated space where you can ask your questions directly to Alexandre, who's going to be today's presenter. If you prefer, you can also scan the QR code on this slide to access the Q&A on your phone, for example. And while you are in the Q&A section, you will also find a short survey about today's webinar in the polls area. Feel free to complete it at any point during the session. We will also send you the survey link after the webinar, so you can fill it out later if you prefer as well. Finally, we encourage you to visit the guidelines and resources section on the event website. There you will find useful links to Help Center articles and several interesting parts of the Copernicus Marine website. Now let's take a look at today's agenda. We will begin with a short introduction to the Copernicus Marine Service, followed by an approximately 1 hour and 40-minute tutorial demonstration led by Alexandre Aumerin from Noveltis. Don't worry, we've planned a well-deserved 10-minute break a little over an hour in to give everyone's brain a chance to cool down before it starts overheating. So without further ado, let's start with a short introduction to the Copernicus Marine Service. Copernicus is the European Union's Earth Observation Programme. It was launched in 2012, and it's now one of the world's leading sources of operational environmental data. It provides free and open information on the atmosphere, ocean, land, climate change, emergency management, and security. All Copernicus services share the same objective, delivering reliable, long-term Earth observation data accessible to everyone at no cost. Today, we will focus on the Copernicus Marine Service implemented by Mercator Ocean, which provides high-quality, regularly updated ocean data describing the physical ocean, sea ice, and marine ecosystems in support of science, policy, and industry worldwide. The Copernicus Marine Service portfolio is built on three complementary sources. Satellite observations provide global coverage and continuous monitoring, while in situ measurements from buoys, floats, and research vessels deliver local precision. Together, these observations form the foundation for validating and optimizing the ocean models produced by the service. As a result, the Copernicus Marine Service offers a vast catalog of ocean products, including real-time conditions, historical reanalysis spanning over more than 30 years, and forecasts for up to 10 days ahead, with coverage of the global ocean and key European regional seas, making it a great resource for both research and operational applications. The Copernicus Marine Service data supports a wide range of sectors, from service and innovation to coastal monitoring and policy development. We group these applications into 12 blue markets, aligned with the three pillars of the UN Sustainable Development Goals: environment, society, and economy. These examples show how marine data translates into actionable knowledge for decision-making. To describe the ocean fully, we organize variables into three families. The blue ocean represents the physical processes such as temperature, salinity, currents, waves, winds, and sea level. The white ocean covers sea ice variables like ice concentration, thickness, velocity, and age. And the green ocean contains biogeochemical and ecosystem indicators, for example, chlorophyll, nutrients, oxygen, carbon variables, or pH. Together, these three families provide a comprehensive view of ocean state and health. And today, as you can imagine, we will focus on blue and green ocean variables. So how do you access all this information? Everything is available through a single portal, marine.copernicus.eu. After free registration, you can browse and download from the data store our harmonized data sets, mostly in NetCDF format, making them easy to use across scientific and operational tools. From the home page, click Ocean Products to open the catalog. And last but not least, beyond downloading data, you can explore it visually using our online tools accessible via the Ocean Visualization tab. Copernicus Marine Service offers 3 visualization tools, each tailored to different needs. My Ocean Learn is perfect for education and outreach. You can explore ocean variables on the globe with rich ocean literacy content, videos, and simplified views. My Ocean Lite is ideal for quick interactive exploration of the essential ocean variables like temperature, currents, ice, pH. You can access live data, zoom into regions, view forecasts, and share. And My Ocean Pro is dedicated for advanced analysis. You can dive into detailed data sets and choose the ones that fit your purpose, depending on how they are produced. Perform custom queries, export data, and access high-resolution graphs for research and professional use. So that's it for this short introduction to the service. We encourage you to visit the website for more information. And now the part that you've been waiting for. I will now hand over to Alexandre Omrin from Noveltis, who will start with an introduction to today's Python tutorial. Alexandre, I can see you. Can you hear me?
Yes, I can hear you, Marine. Thank you.
Okay, great. So I will stop sharing my screen and the floor is yours.
Thank you very much. So hello everyone, I'm Alexandre Omrin from Noveltis, and I will be your trainer for today's session. So let me just share my screen and we'll be ready to go. Okay, my screen should be visible now. Can you confirm?
Yes, thank you.
Perfect. Thank you very much. So yes, so today's topic is climate change for this session and how to use Python to analyze related data. In the frame of this case study, we're going to study sea surface temperatures. So climate change is, of course, profoundly transforming the world's ocean, affecting many variables. And one of those who is the most affected, of course, is temperature, and more precisely, in our context, sea surface temperatures. So surface temperature have a very influence influence on several processes in the oceans, sea-air exchanges, large-scale biological activity, ocean circulation, and so on. So this is why surface temperature are very strong indicator of the changes related to global warming. And our case study will be centered around the Black Sea. So we've chosen this area because it's quite an interesting one. It's a semi-enclosed basin with limited exchange here to with the Mediterranean Sea. It's quite isolated. We have some river input in the north around this more shallow plateau here. And also it has a relatively small size, which makes it more practical in terms of file management and file sizes. But still, the physical characteristic make this area quite telling when it comes to detecting long-term trends and seasonal cycles. So in this case study, the idea of today's session is to show you how to use Python to perform climate data analysis. So we're going to use Python and several command libraries such as Xarray, NumPy, or Matplotlib and Cartopy to work with oceanographic data from the Copernicus Marine Service catalog. So as Marine mentioned before, so it can be divided into three categories: blue ocean, green ocean, and white oceans, with several variables to be analyzed. And we're going to work with NetCDF data, which is a file format that is very commonly used in the scientific community because it is a self-describing file which comes with a lot of metadata that allows any user to have the hands-on information on the data that they are analyzing. So you'll see that we use several of those files in the later sections. So just to remind you of the goal of the notebook, it's a step-by-step guide through the analysis of SST data. And we start with very basic data manipulation and we progressively build towards more advanced diagnostics and manipulations. So if you're following this with Binder Hub, you probably also have access to this notebook, and I strongly encourage you to execute the notebook at the same time as me, because you will see that there are some practical exercises that you can do, and well, it will be more practical if you are at the same point as I am when I give you time to do the exercises. So, as I said, we will be working with Python. So if you're not very familiar with Python, here are a few key points that explain why it is so commonly used in the scientific community. So first, it's a very readable syntax that's very easy to learn. It has a very powerful scientific ecosystem with several libraries that are freely available and easily installable. It has a strong community support with any library is very well documented, and we have countless examples of code uses that we can use to help ourselves code. And Python scripts and notebooks are very easy to share and are easily reproducible. So, which is why you will see that in our context, Python is very practical to manipulate gridded data sets, especially NetCDF data, which you will see in later sections. And finally, if you're not familiar with what the Jupyter Notebook is, it is actually the file that I'm showing you right now. So basically, it's a notebook that combines text and code. So here, for instance, I'm showing you the text part of the notebook, but you will see in later sections that we have some code cells here that we can execute within the notebook. So it's a great way, especially to do tutorials like this one, but also to share code, to share methods. So Jupyter Notebook is a very great tool. And if you're working here with on the Binder Hub interface, to make this notebook work, make sure that on the top right-hand corner here, you have the Python 3 kernel activated. This will allow you to be able to execute the Python code that is in the notebook. Our calculations. So NumPy is a library that is present in almost every Python script ever. It's very widely used in scientific computing to process arrays of data. Xarray is the library in Python that is used to process NetCDF data. As you remember, NetCDF is the main file format provided by the Copernicus Marine Service. So it allows us to process data that is structured as with several dimensions, such as with latitudes, longitudes, time coordinates. So in Python, all of this is usually processed with Xarray. Then Matplotlib and Cartopy are two libraries that are used to draw maps and graphs. So we're going to use them to visualize our data and our results. And finally, SciPy is a very also big library in Python that is used for scientific computing. It comes with a very vast variety of tools for statistics, image processing, interpolation, and so on. And so in this notebook, we'll just rely on this to identify patterns in our data. And we'll use that towards the end of the notebook in the more advanced operations. So first, you're working with Binder Hub for the first time, and the SciPy library is not already installed on the Binder Hub. So executing this cell here, it should install you the SciPy library, and then you should be ready to execute the rest of the notebook. Then in the next cell is the cell where we import all those libraries to have them ready to use in the notebook. So just execute this cell. And then we can move on to the sea surface temperature data that we're going to use. So we'll be working with Copernicus Marine Service data on the product dedicated to Black Sea physics. So if you remember the introduction done by Barine, it's a blue ocean product, and it's called Black Sea Physics Reanalysis. So from the notebook, you can click on the link to visit the dedicated Copernicus Marine Service page on the product to have more information on how the product was generated and all the details such as spatial resolution, all the variables that are available, etc. So you can see we have mixed layer level, seawater temperature, we have salinity also. And so basically this product is a long-term ocean analysis over the Black Sea, produced with an ocean model and adjusted using actual satellite observations. And among those variables, we will focus, as I said, on the sea surface temperature. So yes, I said it's a long-term series from 1993 to the present, basically. As we are studying climate change, it's important to have such long time series because usually in climate science, you usually work with several decades of data in order to identify the long-term trends followed by the data, which is why we're going to to download 30 years of data. And as a spatial resolution, this is equivalent to approximately 2.5 kilometers. And the dataset has 121 depth levels. And of course, we are only going to retrieve the level closest to the surface because we are retrieving sea surface temperatures. So in order to access data, we mentioned that before, but we are going to use the Copernicus Toolbox, which is a tool that is provided by the Copernicus Marine Service and allows us to retrieve data from their catalog. So first, you need to activate the toolbox, so import it in the notebook, Copernicus Marine, and then the first thing to do in the notebook is to use the login function of the Copernicus Toolbox. This will actually create a credential file in your local repository in this Binder Hub. So you just have to enter your credentials. So mine is already present, so I actually don't have to do it. But once you do it, you have this credential file, and you will have access to the Copernicus catalog without having to type your passwords each time you want to retrieve data. Then the function that we're going to use to retrieve the data is the subset function. So this function has a dedicated documentation on the Copernicus Marine Service website. So we can visit the page to have more details on how to use it. And in order to use it, we have first to write a data request that we're going to send with the subset function. So as you remember, we want temperature data at surface level from 1993 to 2023 because we want 30 years of data. And we're going to use monthly values because it's a sufficient temporal resolution to perform the analysis that we have planned. So to write this request, we have to fill in this formula here. First, we need to find the dataset ID. So you remember that we have a dedicated page here on the product. We have a data access tab here. And then we have several sub-datasets available. And here we want to find the monthly temperature here. And we have the ID here that we can copy and paste it here. We want to retrieve the variable name, which is the temperature. So you can click on Form to have more detail here. You can see the variable name is written here. So copy it and paste it in the variables item. Then you need to set up a start date and an end date for the retrieval of the product. So here we've defined them here. So beginning of 1993 toward the end of 2022, 30 years. We want to specify the depth level here. So it is the exact level of the closest layers of the surface, which is 50 centimeters. So write the same for minimum and maximum depth. And finally, output directory. So you want your product to be downloaded in the data repository here.
Alexandre, we have one question that I just wanted to ask you before you go further that we got on Slido. Someone says, I can't edit the username and password in the notebook to log in and download the data. Any suggestions? Do you have any?
Well, make sure that you execute this cell. It should let you write your own credentials. So either you can click on the triangle here, and it will show you this input here where you can enter your credentials. And if this doesn't work, that's probably a problem with the Binder Hub, maybe, because it should work.
Okay. Well, I think if that's fine, then you can continue. Thank you.
Yes, maybe it's not very clear that I'm executing the cells because I'm not clicking on the icon. I'm just using a keyboard shortcut to do it. I'm typing on the Control and Enter to execute a cell. But if you're not at ease now, you can just click on the run icon here. It will execute the cell, and you can do it successfully to execute everything. So I'm just going to move on, and don't hesitate to tell me if
Yes,
there is
please.
we have to go back on this issue. Yeah.
Yes, please go on. Thank you.
Okay, so as you can see here, we have successfully downloaded the product. You can see that it is in the data directory here. So I've executed cells several times, so you can see that yes, I have some doubles here, but my netcdf product is present. And now using Xarray, I can open it. So copy the file path in the cell. And when you open it, you will have this output here, which we can explore very quickly. So we can see that we have 4 dimensions here. We have a time dimension. You can click on this icon here to show a sample of the data, and we can see that it goes from 1993 January to 2022 December. As this question notices, so there is a way to display the temperature variable metadata and check the unit of the temperature. So the temperature is here. You can see that it is related to time, depth, latitude, and longitude. So it's along the 4 dimensions here. And on this icon, you can show additional metadata on any variable. So it's here temperature, but you can also do it on the others here. So you can see that it's actually, yeah, the long name is temperature. It's in degrees Celsius, so that's a very key information. And has also a standard name, but here we've managed to find the unit of the temperature, so it's in Celsius and not in Kelvin, for instance, which is also quite common in temperature data. And then finally, we have some additional metadata related to the product. So with the conventions that are followed, some contact information, external titles, several external links to for additional resources or for the institutes that provide the product, namely Copernicus Marine Service. And first, you can see that we have this depth dimension here that we want to erase because it has only one item, because it's only the surface level. And if we keep this 4th dimension in our dataset, it will likely produce errors in later analysis. So we want to simplify this using the squeeze function. And now that we've done this, you can see spot the difference with the previous display of the dataset. You can see here that the 4th dimension depth has disappeared. It's still here, but you can see it's empty. And now our temperature is only related to time, latitude, and longitude. So now we literally have a dataset of sea surface temperature. So this is the first simple pre-processing of data that we have successfully performed. So now we are ready to manipulate the sea surface temperatures. So first, one essential manipulation that is useful when processing such data is to calculate an average across the entire time period. So to do this, we can use the min function from the Xarray library in order to perform the SST data over the full 30-year dataset. So basically, you just use the min function and you make sure that you do it across a time dimension. And in the output, you can see that the time dimension has disappeared because it's a dimension along which we've performed the average. And so we have a 2D map of the sea surface temperature over the 30 years of 1993 to 2022. And this 30-year average in climate science is usually called climatology. So this climatology will serve as a reference for later calculations. But first, what I would like to do now is to visualize on a map this climatology of sea surface temperature in the Black Sea. So first, I'm going to show you step by step how to draw a map in Python using Matplotlib and Cartopy. So first, of course, you need to define the coordinates of the corners of the map. So you define a minimum, maximum latitude and longitudes with this cell. Then you initiate the map, so it will just build a figure and axis object. So first, for now, it's only a blank rectangle, but we're going to fill it with geographical characteristics. Then we can add some geographic context using Cartopy. So here in those lines, you can see that I'm adding coastlines, the country borders, grid lines, and so zooming in on the box that we have defined previously. So you can see now that we are indeed centered around the Black Sea. So with this cell, I'm just copying those lines in the Python function so I can reuse it in a single line later on because we're going to draw many maps in this training. So this is just to save this drawing. And finally, we are ready to use pcolor mesh here to color the map according to the sea surface temperature data. So you can see that I'm defining the coloring with the latitude and longitudes, so the two spatial dimensions, and coloring it using the SST field. Here I'm defining a color map and some boundaries for the values. So here I have my average temperature over the 30-year period. And finally, I can just add some titles and the context to have a better readability of the map here in this cell. So you can see that I have added a color bar here using the color bar function from Matplotlib, and I have added a title. So it's a climatology of sea surface temperature on the Black Sea from 1993 to 2022. And we can see that we have quite a smooth pattern here with a cooler temperature here, probably because of the river inputs that we have here. And here it's a more isolated area. So we can see a nice gradient here of temperatures across the area. And so now in the later maps that I'm going to draw, I'm just going to do these steps all in a single cell. So I've just copied every step here in a single code cell. And so this is a one-shot drawing of the average SST map. Okay, next, I'm going to show you another essential feature of the Xarray dataset, which is the cell function, cell for select, which allows us to subset the dataset along a given dimension. So in this example, I'm subsetting the dataset along the time dimension, and here I'm actually selecting a single year of data. Here in this example, it's 2005, but it can be any year. So using a set function, I specify the time dimension and specify 2005 as a string here. And you can see that in the output, I have only 12 values remaining because we have only 12 monthly data, so 12 months in 2005. And here you can see that I have my 12 values, one for each month of 2005, and I still have my temperature here across the 3 dimensions. So it's quite easy to use. You can also, I'm going to show it to you quickly live. You can also select a range of data using the slice method here within the cell function. So for instance, I want data from 2005 to, let's say, 2007. And you can see here that I have this time 36 time steps remaining in my output with data from 2005 January to 2007 December. So this is good to remember when you want to select data within an existing dataset. And of course, this also works on latitude and longitude. So now we know how to select a single year of data we have computed a reference climatology over the 30-year period. So with those two things, we are able to compute SST anomalies. So an anomaly in climate science is the deviation of, let's say here, yearly SST temperature with regards to the reference period, which is our 1993-2022 climatology. So first, we want to calculate the average temperature only in 2005. So we redo the mean function here, but on the 2005 dataset. And then we simply subtract the climatology to this new dataset to have the anomaly of 2005 in terms of sea surface temperature. And you can see that we have indeed a two-dimension dataset, so it is easily visualizable on a map. And which is what I'm going to do now. So you can see that I'm initiating the plot, creating the basic geographical context here, and using p-color mesh to plot the anomaly and then adding a color bar, etc. And here is my 2005 climatology. So now I propose to you an exercise if you are executing a notebook at the same time as me, is to plot anomalies for other years. Here are the outputs that you should obtain for each of the year of the time period that we have available. So I'm just going to give you 5 minutes to try to reproduce the analysis on another year and see if you can get one of those maps here. So yes, I will come back in 5 minutes and yes, we'll try to see if have your feedback on if you manage to do it or not.
Thank you, Alexandre. And if you have any questions that you'd like to ask regarding the first part that we just went through, don't hesitate to ask them through the link that was just shared in the chat. We've already received some questions that I think we can maybe answer in 1 or 2 minutes just to give some time to people to actually focus on the exercise and run it. But yeah, just to let you know, Alexandre, we already have a few questions to answer.
And just for notice, in the next cell, there is an empty cell here that you're supposed to fill in for this exercise with a few guidelines to help you go through with this. So don't hesitate to use it to plot the anomalies that you want.
Okay, I suggest we start answering the questions that we've received already on Slido. So what I can do is I can read the question out loud for you, Alexandre.
Yes, I'm trying to read the Slido with you so I can anticipate. So yes, which question do you think I should
So the first one we received was, is there a way to print in the same Python console all the codes available in the database, or we need to access the website to find the code and the variable name no matter what? Sometimes it might be more practical to do it directly on the script.
I'm not sure I understand the question actually. I mean, what code and what database is the user referring to? I'm not sure I understand.
So if the person who asked this question want to give us a bit more detail about what you meant when you asked it, the question is highlighted on Slido, so you should be able to see it and add
Yes,
precisions
I
if you'd
can
like.
see, yeah.
So, okay. Second one we received is it possible to use the sea currents data to plot the currents? And if yes, can I use the data to calculate the time travel between two sea points following major currents?
Yes, you probably can at least have with a simple model of displacement using seawater velocity and yeah, the distances between the 2 points. You can retrieve the time travel, but it will be only I think a simple approximation because when a point is traveling through a water current, there are probably other processes that influence its trajectory. So I think using currents data would give you an approximation, but it would probably not be a real, sorry, a very accurate indicator of the actual trajectory. If you're referring to a real life point, to real life points, I think.
Okay, thank you. And the third question we received is, I am more used to working with environmental data in RStudio. I would like to ask if there is a way, for example, a toolbox similar to Python's, to open netcdf files directly in RStudio, or if this is something planned for the future.
Yes, there are libraries in R that allow you to work with netcdf data. So I'm less familiar with R than with Python, for instance, but we have colleagues at Noveltis who do trainings also here with the Copernicus Marine Service who provide R tutorials working with netcdf data. So I think they are probably in the Jupyter Notebook database R tutorials that use such libraries. So maybe you can refer to that to work with the same data sets, but with R.
Okay. Oh, actually, we got one new question, which is to evaluate the effect of climate change in temperature in the long term, what database can I use? I think it's a very vast question.
Yes. So I don't think on the Copernicus Marine Service that there are climate projections data available. But on other services, you can find some predictions made by models. I know that in the ECMWF, you can have CMIP5 data, which is which provides monthly climate projections. So perhaps you can refer to such data sets to do the work you intend to do. It's also publicly available. And yes, I think it provides several simulation from the that were used for the IPCC, so the Intergovernmental Panel on Climate Change. And it provides you with several scenarios of CO2 concentration in the atmosphere. So you have a lot of data sets available, and you can have prediction from several hundred years in the future. So you can refer to such data set, I think, if you want to study future projections.
Okay, great. We haven't received any other questions, so I think you can
Maybe we can
proceed
move on to
yes.
to show just a quick solution to this.
Yes, please.
So we actually don't have many things to change from from what I've shown you in the previous cells. So the only thing to do is to choose another year of data using the cell function here that I had shown you before. No, it's not here. It's here. So I'm just going to reuse this and average the temperature over this new year. So for example, I'm choosing 2012 here. Okay. So now that I've done this, I have to compute the average over this new year. So I'm just going to sorry, I have it already copied somewhere, so I can go quicker using just copy and paste here. Yes. You can see that performing the mean across the time dimension. And then I have to compute the anomaly using the climatology that we already have. So the anomaly of 2012 will be this average temperature over this year minus the climatology of the 30-year reference period. And finally, I just have to visualize it using pcolor mesh. So the function that we have used here. Make sure that this time it's the anomaly from 2012. Same color, etc. I don't have to change anything here. And then remember just to add the color bar and title. And we should have, just need to correct the year number in the title. And we have here our 2012 climatology, and we can see that contrary to 2005, in 2012, temperature were much warmer than the reference period over this year. And you can see that it's consistent with the solution here. We have this spot here in the middle, and we can see it here also. So, and you can perform the same operation on any year you want to explore a little bit the data. All right. Do you have any questions, or should I move on?
We just received one last question, which I
Yes.
think is very short to answer. And it is it possible to download seawater temperature at different depths?
Yes. If you remember in my data request here, we have minimum and maximum depth items. So, well, can I select this? Yes. So you can see here in the Copernicus Marine Service page that we have several levels of depth available. So you can go to several thousands of meters under the surface. So basically you can just play with this range here. So you can increase, for instance, the maximum depth and you will get data on several depth levels. So yes, you can definitely adjust that when retrieving data from the Copernicus Marine Service.
Great. Thank you very much. And we don't have any other question at the moment, so please feel free to continue.
Okay. So moving on to the next section, which is the sea surface temperature time series. So time series is a very common way also of studying oceanographic variable because in a single glance we can track changes that happen over time. So this time it allows us to summarize the evolution of temperature across an entire region, which is what we're going to do here on the Black Sea. So first we need to convert our temperature dataset into a time series. So basically what we're going to do is to use the mean function here, but this time we will compute the average over the two spatial dimensions, longitude and latitude. And as a result, we will only have the temperature along the time dimension. So it's the average over the entire area. And you can see that we have still 360 time steps. So each month from 1993 to 2022. And so we have our time series. I propose to you that we visualize it to see if we have any temporal patterns in our monthly data. So first, here in this cell, I'm quickly showing you. So I just retrieve the values of temperature. I retrieve the values of the time steps. I make sure I convert them to a datetime 64 format, which is a common format in Python that is easily read by the matplotlib. And then I just set up my graph here using the plot function. I'm just arbitrarily choosing to plot it in orange and then I add titles and labels to the graph. And here is my result. So those are the sea surface temperature of the Black Sea from 1993 to the end of 2022 on a monthly resolution. And we can see that we have a very strong seasonal variability, which is what could be expected, of course. But the problem is that with this strong seasonal variability, we can't really see any obvious long-term trend. So a way to erase this seasonal variability is to simply resample the data to yearly average values, which will remove this seasonal oscillation. So I'm going to show you a first way to resample an accelerated dataset, which is using the resample function. So using this resample function, we use the resample time set, which is 1 year. And to have yearly average values, we just call the mean over the resample object. And then we can replot our yearly values this time. And you can see that this time we clearly see that there is an increasing trend in sea surface temperature in the Black Sea in the last 30 years. So the trend is much clearer. And so simplifying the data sometimes allows us to focus on aspects that are not very visible when we have the full data set. And in the next section, so we have this qualitative view here, and the next section we will try to estimate it in a more quantitative way by performing a linear regression using the least square method. So this is what we're doing in this section. So the goal here is to provide an estimation of the increasing rate of the sea surface temperature in this area. So looking at this curve, it seems that linear regression could be a good fit for this curve. The idea is to be able to express the mean temperature as a function of the year with a single coefficient and of course an offset here. A is usually called slope and B is usually called the intercept of the linear regression. And to do that, we're going to use the polyfit function from NumPy. So Python provides a vast number of functions depending on the library to perform this operation. So this is purely an arbitrary choice. It uses the traditional least square method. The goal is to minimize the residuals between the trend line and the actual data points to find the line that best fits the data. So first, to do that, we're going to retrieve the years that we have in our data. So you can see it goes from 1993 to 2022. We have 30 years of data. And then we retrieve the average temperature values for each year. Here they are. And then we can call the polyfit function using the two variables that we have retrieved here. Make sure it's degree 1, so it is a linear regression. So polynomial of the first degree. And the slope, so the A coefficient here, gives us the warming rate of the data, which is here 0.60 degrees Celsius per decade. Small exercise for you now would be to try to plot this trend line over the yearly dataset that we have plotted before here. So you have all the tools that you need to plot this trend. So here is a template here that you can fill in to make this new graph. So I'm going to just give you 5 minutes to try to do that, and I'll come back and show you a quick solution. So good luck to you, and in the meantime, we'll try to answer questions if there are some.
Yes, we have received 2 or 3 questions. What we can do is maybe wait for 1 or 2 minutes before we
Yes.
start answering these.
Okay.
Okay, we can try and start answering some questions.
Yes.
So once again, if you have any question, you can post them on the link that was posted in the chat. The first one we received is, what do we have to watch out for if we want to change the variable that we study? For example, if we want to study about the wave height of the Black Sea.
First, you need to make sure that the variable is available in your dataset. So, sorry, I'm going to go back to my data requests. So if you remember here, I've specifically requested for temperature data. But if I were to analyze, let's say a wave, a significant wave height, I'm not sure if it's available in the same product, but for the sake of the example, let's just say I want to study salinity, for example. So I can see that in the data access tab, I have another ID here, identifier for the salinity data. So in order to retrieve salinity data, I'm actually going to show you that later on, but retrieve the ID and make sure that you have retrieved also the variable name here. And then you can modify your data request in order to retrieve the salinity here. And this works for any of the variables. For the currents here, you should have probably several data sets available. So here, for instance, there are two variables that you can retrieve from this data set. So the eastward water velocity and the northward water velocity. So yes, first make sure it's available and that you have downloaded it. And then when you're working with the data, you usually select the variable that you want to analyze. So here we have this one. You can see some of my code cells. For example, here you can see that when I plot the temperature, I specify it here in the code. So basically, you just have to make sure that you're using the right variable name when you call for data values in your code.
Great, thank you. We just have one other question, which is considering the amount of data requested for a certain range of depth, what is the quickest way to get data with a min and max depth between, for example, 0.4 and 0.6? I try to fetch the data, but it takes a lot of time and it works a lot on my CPU.
Yes. Well, actually, using the Copernicus Toolbox Python API here, like I'm doing in this tutorial on the Binder Hub, is one of the quickest ways I've known to download the Copernicus Marine Service data. And of course, yes, depending on the area you're working on and on the number or depth level that you are trying to retrieve. It can indeed be very heavy to download. So in the case of the Black Sea, with only surface level data, I think we actually have quite light data sets. I don't know if you can access the actual size of the data, but it's all working pretty quickly. But I think the depth level that you're specifying, so between 0.4, 0.6, I'm assuming it's meters. You should be very close to the surface level. So I don't think you should have many. I don't think it should be a lot heavier than what I'm working with. But perhaps you are currently working on other areas than the Black Sea that are probably wider and require more, I don't know, data space and CPU power to process.
Okay, yeah, so the answer is the toolbox that you're using in this tutorial then.
Yes, it's the quickest way I've worked with until now to download data. I mean, it's taken me only a few seconds to download quite heavy data sets, so it works quite well in this environment.
Okay, great. We just received another question, which is what if we want to analyze or download a few parameters at the same time from the same data set? How can we do it?
Yes, so that really depends on the product that you are working with. So you can see here on the Black Sea Physics reanalysis, every variable is separated separated with each single data identifier. So with this product, you actually have to download each dataset separately. So there are not many modifications to do to your data request to be able to download everything. But as I've mentioned before, you just have to change the ID and the data name several times for each data that you want to retrieve, and you'll have one file per variable in your data directory. But for other products in the Copernicus Marine Service, there are actually products that provide several variables in a single ID like this. And this time, your netcdf file here, you'll have several data variables available in a single file. But that really depends on the product structure provided by the Copernicus Marine Service. So it's it's case sensitive, so there is not a universal rule. It really depends on the product that you're working with.
Okay, great. Thank you. We don't have any other question to answer at the moment. So if you want to go back to the exercise
Yes.
and give the answer.
Yes, so it's not too difficult. So the idea is to generate a common plot of a trend line above the actual data, which is very commonly done in scientific computing. So if you remember, we wanted to model the data as a single degree of polynomial. So a function of the years multiplied by the slope plus an offset. So we just have to rewrite this expression, but as code, actually. So we need to find our A coefficient, which is the slope. It is the warming rate actually. So, and we want to build our values, our value list using this. So remember that we need the years that we had retrieved before. We multiply it with the slope variable here that we have computed using the linear regression. And we add the B coefficient, which is the intercept. And now our values of the trend line should be computed, and then we must make sure that we can plot it on the graph. So we need to complete this function here. We have also a to-do commentary here. So we can inspire from the previous plot here. So this time we want the trend values. It's not that like this. It's the vals trend variable name. Just choose a color, let's say blue. And let's say I just want to have a dashed line for the plot. And it should give me a nice trend line here. And I can also add a label. And it is displayed here. And so this is a very common plot in scientific computing and yes, data analysis and modeling. Okay, so in this section, to end this section, I'm just going to show you a quick, more advanced plot, which is mapping the SST trends, but across the entire area. So I'm going actually to do the same operation, but on every single pixel of the map where we have data available, of course. So this time I'm going to also resample the dataset to yearly values, but this time at every point of the map. So I'm going to use a different function for the resampling, which will be more practical for this particular context, which is the group by function. And I'm going to group the data by year and still compute the yearly average values. What's interesting here is that in my new X-ray dataset, the time dimension has actually changed to a year dimension, which is caused by the group by function, which is why I've used it. It's more practical for the later manipulations. And then I can use also the polyfit function from this time built over X-array, but like it's exactly the same function as NumPy, but adapted to the X-array dataset to perform it across the year dimension, and it will perform the regression over each latitude longitude point of the data. And when I do this, you can see that I have a 2D dataset. So I have my map, and for each pixel, I have so a polyfit coefficient variable, which actually gives me for each pixel the slope and intercept, so my A and B coefficients. And so now I can plot the warming rate at each point of the map by plotting just the slope values on a map. So now you know how to draw a map, still using the p-color mesh function. And I'm selecting the slope, not the intercept. This is not necessary here. And I have my SST trends in degrees Celsius per decade. And you can see that the warming trend is quite homogeneous here over the entire Black Sea, which is quite expected because first it's a relatively small area, and it has very limited exchange with the Mediterranean Sea, which and it has relatively consistent atmospheric forcing. So we have some local variations, but the overall increase in surface temperature is very similar across the entire basin. All right, so we are ready to go to the next section unless there are some questions. If there are
No,
not, perhaps
no
we can move on.
questions.
Sorry?
Yeah, no questions. You can move on.
Okay. So yes, I don't think we have time for a coffee break now. So I just move on.
Yeah, sorry. I think let's consider we had the coffee break at the
Yeah,
start,
we had the
and
coffee break at the beginning. Yes.
yeah, we're a bit late. So yeah, let's
Yes, I'll
continue
try
if that's okay with you.
yes, I'll try to be as efficient as possible.
No problem. Thank you.
So here's a quick section on correlation of the sea surface temperature with other variables, because when studying oceanography data, it's quite interesting to see how different variables interact with each other. And here in this first example, we're going to see how the sea surface temperature interacts with salinity data. So to do this, we are going to use the core function of the X-array library to compare the salinity and temperature datasets. So if you have followed, you probably seen that in our same product, Black Sea Physics Analysis, we also have monthly salinity data. So this is great for us because we are going to compare two variables that come from the same product. So the two grids are aligned. We don't have any interpolation work to perform. So we can compare the two datasets without any further preprocessing. So you can see that this time I'm retrieving the salinity data. The variable is written as SO, same depth levels, same start and end dates, and same directory. You can see that it's only taken me a few seconds to download the data. And I have my new data set here. You can see it was created 15 seconds ago. And when I open it, it has exactly the same structure as the temperature dataset. So I've already used the squeeze function to remove the depth level that we don't need. We have the same structure, same number of time steps and latitude and longitude coordinates. And we have our salinity variable that we can explore. So this unit is basically grams per kilogram of salt per water, per liters of what per kilogram of water, sorry. And the idea now is to draw a correlation map between sea surface temperature and surface salinity. So as mentioned, we are using the core function of X-array, and we are correlating the temperature from the temperature dataset and the salinity from the salinity dataset across the time dimension. And you can see that we have a 2D map of correlation values. So here we can only see NaN value, so it's called not a number, because on the corners here we actually don't have any data values. But we do have correlation values within this data here in the suspension points. And now we are ready still to reuse pColorMesh to draw the correlation map. You can see here I'm plotting the correlation values that I have just computed. And here is our result. So we have quite a smooth and quite homogeneous correlation map here with slightly negative correlation between sea surface temperature and salinity and surface salinity in most of the area. So this is a result that invites us to do some more investigation to understand why in our data sets we have basically lower salinity when we have higher temperature and vice versa. This is why you have a negative correlation. So let's just plot the time series of the sea surface temperature and the salinity to see if we can explain these results by looking at the monthly dynamics of the data. So comparing the two time series here. So you had already seen on this side the temperature data that we had plotted in the previous section. And here we have the salinity values. We can see that from the 2000, we actually have a strong increasing trend in the salinity. But what's more interesting here is that the seasonal cycles of the two variables seem to be inverted. You can see here, for instance, that when the salinity decreases, the temperature increases and vice versa. So this is quite interesting, and this is also an expected behavior actually, because when we have warmer waters, this enables surface eutrophication and more freshwater inputs that influence salinity. And this is why we have a lag between the seasonal cycle of temperatures and the seasonal cycle of salinity. So this is why we have this negative correlation using monthly data. But now let's see what results we have when we use yearly temperature and salinity values, because we can see that if we remove the seasonal pattern here, we will probably have different results. This is what we do here. We reuse the resample method that I've shown you in the previous section. And then we compute the yearly correlation using the same function from Xarray. And this time, drawing my correlation map, we actually see that we have a very homogeneous positive correlation across the entire Black Sea. And we could see it in the time series that we had a strong increasing trend in the salinity. And we know that we also have it in the temperature. We've seen that in the previous section. So this is why across most of the basin, we have very well correlated temperature and salinity data, because both follow an increasing trend in the last 20 to 30 years. Okay, so I'm going to be a little quicker on this subsection because we are going to do exactly the same thing on another variable, this time primary production. So basically primary production reflects the rate at which phytoplankton converts inorganic carbon to organic matter. So it's a very strong indicator of the biological response of the ocean to environmental condition. So this time we're using another product, which is the Black Sea biogeochemistry reanalysis. So it's from the same provider, so we won't have any pre-processing to do. But this time it's a green ocean product because this time we're using a variable that refers to the biological activity in the Black Sea. So same thing as usual, go to data access and find the variable that you want to retrieve. So here we're using the monthly primary production here. So we copy it here. This is the name of the net primary production variable. Same start and end date. Make sure that you have retrieved the exact depth level for the surface. Takes a few seconds. Yes, 2 seconds. You can watch the data set. So it's also been pre-processed. We have still 30 years of data in monthly values. We have the same number of coordinates. So this is a good indicator that the two data sets will match regardless. And so now I just quickly resample it to yearly values and compute the monthly and yearly correlations to see if we also get different patterns depending on the temporal sampling of the data. And I draw the two maps. And you can see here that same thing as the previous case study of salinity. We have very different results depending on if we correlate monthly data or yearly data. So first, in the monthly data, we have positive correlation between the temperatures and the biological response in the north of the Black Sea, but we tend to have negative correlations in the south of the sea. So this is probably due to favorable growth conditions. We probably have a lot of nutrient inputs from the rivers here, especially near the coast. This is very visible. And we have some negative correlations here, probably due to seasonal limitations on nutrients. So I think the biogeochemical physical analysis provide nutrient variables. So if you're interested, you can also retrieve this data to check on this hypothesis. But when we switch to yearly data, you can see that we have very strong negative correlations between the two variables. So this time we have removed the seasonal cycle. And so this reveals a quite expected effect is that the warmer temperature tend to reduce the overall productivity in most of the basin because we have limited nutrients. But we can still see that in coastal region, those are areas that are still more favorable to phytoplankton growth. Because it's probably in those areas that we still have nutrient availability. So yes, this shows quite a strong impact of global warming on biogeochemical activity in the Black Sea. So here I've proposed an exercise, but I don't know, Marine, if we should move on or still give time to do it. But the idea is to retrieve another variable from the products to perform any correlation that you would like to perform. So, Marine, what do you think? Should we move on or should we still give time for this exercise?
How many exercises do we have after this one?
We have two after this one.
Okay. I think, maybe.
I think it's the one that is the easiest to move on from because we already shown two examples, so it's just a
Yes.
matter of repeating the operation.
Yeah, okay. So yeah, maybe leave this one for now. We will make sure to send you the tutorial with all the correct answers after the event. So leave this one for now, and we'll have more time for the two remaining. And I know the last one is quite interesting, so I think it's better
Yes.
to keep some time for this one.
Yes, and if when the demonstration video is available, I actually show how to some other correlations to to complete this section, so you can refer to that also.
Can we just take 1 minute to answer a question we
Yes.
received, and I think is a good time now to answer. The question is it possible to compare in a similar way as done now two variables from two nearby pixels, for example, ocean waves and runoff?
Mm, Trying to make sure I understand the question. So yeah, the idea is to compare two data sets, but that show different physical phenomenon. Um, I think in order to do that, you will have to erase the spatial structure of your data set. So I think it would be a similar thing as comparing just the correlation between two random time series, um, which is more simple actually than correlating two dataset pixel to pixel. So yes, I think that's really possible. It's just that it's not exactly the same process.
Okay.
You just have to have the yes. I think if it's ocean wave, perhaps the significant wave height or data on one side, but only the values and the runoff values on the other side, and correlate the two arrays, but devoid of any coordinate information that would probably generate errors in your computation.
Okay, thank you for this answer. And just to go back one last time on the topic of addressing CPU kind of slowness issue. Someone is asking, would it be possible to download data at predefined depth using a for loop or a similar method? For example, I would like the temperature at a depth of 20 meters for point X and at 100 meters for point Y.
Yes, so if you I think, yeah, if you don't have the power or space available to retrieve the entire dataset on the depth level that you need, I would probably, in this context of the Copernicus Marine Service data and Copernicus Toolbox, I would probably retrieve data on a very small area around point X at the surface level that you need. So it's a matter of setting up. Sorry, I'm trying to find data requests. Yes. So yes, I will probably, sorry, I'm going to do that in this request. So with the Copernicus Marine Toolbox, you can set up minimum and maximum latitude and longitudes. So I will probably set up a very small box around your point X, and in another request, set up a very small box around your point Y. So that way we'll be able to download a lightweight sample of the dataset that you need, and then I would be able to retrieve the values at 20 meters and 100 meters for both points. So that would be a workaround if I couldn't download the entire data at once and then pick within the entire dataset the points that I want to retrieve data from.
Okay, thank you. I don't think we've received any other questions, so you can proceed with the rest.
Okay. So moving on to the last section of the training. So this time we're going to do a little more sophisticated analysis of the temperature data because we're trying to build some extreme events indicator, namely marine heat waves. So to detect this, we'll still work with SST data, but this time with daily temporal resolution, because extreme events usually happen in a frame of a few days. So we also have daily data available in the Black Sea Physics Tree Analysis. We had the monthly temperature until now, but we can pick up the daily temperatures. So it's a new ID that you can just request here, same variable name. And this time to keep a file of manageable size, because of course daily data will result in a much bigger data set to download. I will be working in a smaller box in the center of the Black Sea in order to study extreme events without influence from the river inputs near the coast, for example. So to have a more homogeneous sample of the Black Sea sea surface temperature. So I'm defining here this smaller box here, so with those coordinates, and I use them here in my request to retrieve data within this area. Oops, I forgot to execute this cell, and now it should be downloading. So it's a bigger data set, so it takes a little more time to download, but still it will only be dozens of seconds. Exactly. 9 seconds, perfect. And now we can open the dataset that we have retrieved, and you can see that we have a lot more time steps because we had one each day, 1st of January, 2nd of January until the end of 2022. And you can see that we have less latitude and longitude coordinates because we have retrieved data on a smaller area. Quick exercise. So you've learned throughout this notebook how to draw maps. So now you should be able to do a quick visual check on this study area by plotting this new map of the surface temperature, but from this daily dataset. The idea is to actually visualize what is our smaller working area. So you can have 5 quick minutes to try to do that, and if there are some questions to be asked in the meantime, we can answer them.
We just had a question about the products that we've used until now. So I just replied to this question on Slido where it was posted. So
Okay.
whoever asks this
Yes,
question, you
I
can,
see the algebraic. Yeah.
yeah, you can go there and get this information. But you also have the link to these products in the Jupyter Notebook. And we don't have any other questions, so I think we can just let people work on the exercise for a few minutes. I think we can continue whenever you're ready, Alexandre.
I'm ready.
You're
So,
always ready.
so yes, the idea of the exercise is where to finally make you let you draw a map from scratch on a new data set. So first, the idea is to reduce this data set to a 2D latitude and longitude data set. So we erase this time coordinates. So we've seen before how to do that. One possibility is to select one single time step or to calculate an average over the entire area. For instance, let's just select one single day of data to plot. So we'll use a self function that you have seen before. And this time we want to select a single day. Let's say the first day of the data. So 1st of January, 1993. So this has worked. You can check quickly that we don't have any time coordinate anymore because we have a single day of data. And now just draw the map. I can still show you step by step. So initiate the plot, add the basic geographical context, use the P color mesh function to draw the temperature data over the map. So I'm just changing a variable name to have the one that I've just computed. And finally, just add a color bar to better read the data. And you can see here that we have quite a more homogeneous area over this simple area. So you can see that we don't have any data in those areas where we have all the river inputs. So I've chosen a time step in January, so we have quite a low temperature. You can just tweak here with the scale of the color map to have a more contrasted colors here in the temperature data. So yes, this is the area we're going to work with when computing extreme temperature events in the next section. Okay, so to compute marine heat wave, to detect them, we have first to compute a reference and a threshold. And when the sea surface temperature will exceed this threshold, we will be able to label this event as a marine heat wave. So first, as a reference, we'll compute a typical average year of the data for the 30-year period, and then a typical extreme year of sea surface temperature. So for each day of the year, we'll compute the 19th percentile of the daily sea surface temperature. And this will allow us to have a seasonal variability over a typical year, and will give us our threshold as a reference for our marine heat wave detection. So here we compute the time series of the data, so performing the mean over longitude and latitude. Then we group the dataset by day of year. So we group each 1st of January together, each 2nd of January together, and so on until the end of the year. We remove the day number 366 to avoid issues regarding leap years. And we do that. So we've done that for the average, and we also do it for the 19th percentile using the quantile function. Same thing, we remove the last day of the year to avoid leap year issues. And here are our two, I would say climatology, but it's basically in black the typical average year in terms of sea surface temperature. So from day 0 to day 365, so 1st of January to end of December. And in orange, this is the 19th percentile. So this is our threshold, and if we have SST values above this line for a given year, we can say that such an event is a marine heat wave. And of course, also it's a marine heat wave if this exceeding lasts more than 5 days. It's a typical threshold also about duration. So now we should be able to detect marine heat wave events with this reference. So here is the method of detection that we have coded here, but here's a brief series of bullet points to help you understand what is performed. So first, for a given year, so we choose a year, we compute the daily average SST over the area. Then we compare it to our threshold here, our orange line, and we identify consecutive periods above this threshold. So those will be potential marine heat wave events. As I've said before, those events have to last more than 5 days
to be labeled as marine heatwave events. So we filter out the shorter events. And finally, so all we have left to do is to count the number of events and report the longest duration. So this is what is done in those functions. So we have here a small function to filter out the short true runs, and here we have the display of the results, so the year we have chosen, the number of marine heatwave events, and how long the longest of the year lasted in days. So we can test this tool now. So for instance, here I will be using 2019, for instance. So in year 2019, apparently we had 4 marine heatwave events, and the longest one lasted 30 days. So in the next cell, I can show you how to visualize this through a series of plots. So I'm just going to plot the year 2019 over this graph. And you will see here the visualization. So 2019 is in red. And we can see here that this 30-day long marine heat wave is probably this event here, where we can see that the red line exceeds the threshold from here at the beginning of June to the end of June. So this should be about 30 days indeed. We have another event here in between November and December. We have a last one here, and you can look more closely to find the fourth one which was referred to. There is a possibility that we have this exceeding for more than 5 days here, though this is probably the fourth one. So yes, this is a nice visualization and very telling about marine heat waves. And in this last exercise, I will let you use this tool and develop do your own little development to explore the other years of the data and try to find which year was the one with the longest marine heatwave event and which was the year with the most numerous marine heatwave events. So if you can find this, well, it will probably show that you have gotten quite familiar with Python. So there are several ways to perform this exercise. There are some very simple, but I would say time-consuming ways, but there are also efficient ways if you are perhaps more experienced with Python. So I'm going to give you also a few minutes to try to do that, though this is probably a little more advanced. And if you feel that you can do it, you can also plot the yearly counts and longest durations over the years to see if you can visualize any trends in extreme temperature events over the last 30 years. So we'll let you some time to do this exercise and come back to show you a solution in a few minutes.
Thank you, Alexandre. I just want to add, because we're a bit over time, so I just want to say now, if you need to leave, that's obviously absolutely fine. We'll make the replay of the session available on the event website in the coming day. You will also receive a certificate of attendance by email, and we will make sure to share with you the final tutorial with all exercise filled out. So yeah, obviously, thank you for joining. If you have to leave now, and apologies again about the technical issue, but if you have a bit more time to stay with us, we'll go through this last exercise together in a few minutes. Okay, drum roll. Should we show the solution for the last exercise from today?
Let's wrap it up. I'm going to code here in this area. So as I've mentioned, there are several ways to do that. So if you get creative, there are an infinite number of possibilities. So I would say the first thing you think about is the naive way of doing it, which is repeating this execution, but on other years, and note the statistics for each of the year that we have computed. So you can see that in the previous years we didn't have any marine heatwave events regarding to our reference, but in later years we do. But what I'm going to show you is a one-shot method of retrieving the answers for the questions. Basically, we'll be using a for loop. If you're working with any programming language, you're probably already familiar with this structure. So I'm just initializing. Sorry, what? I'm going to be a little more clever about this. So I'm just going to initiate a maximum duration and a maximum count variable that I'm going to edit across a for loop. So first I initiate my year values. Actually, I'm initiating empty lists of max duration and counts and my heatwave counts. And so I'm setting up a for loop over the year values. And for each year, I just have to use my detect marine heatwave function. So I'm using still the daily time series of temperature. The year here is chosen from the loop. I have my threshold here. I'm not printing the results because I don't need to. I just want to save the values in variables. And then I add the variables in my to list here. So at the end of the loop, I will have in this list the count of the number of marine heatwave for each year and their maximum duration for each year. Next, I'm just converting those lists in the NumPy array format. So it's a simple conversion because the format is more easy to use afterwards. And then using the argmax function from NumPy on the two lists, I can actually retrieve the index of the maximum duration of a marine heatwave event. So it will give me the year of the maximum of the longest marine heatwave event. And same thing, using the argmax, I will retrieve the index of the year of which has the most numerous marine heatwave events. And then I can just print the answers here using those two indexes in the list of the year values. So it takes some time to use this function on the 30 years of data. But what I can see here is that 2018, according to my script, is the year with the most numerous marine heatwave events. And 2020 is the year with the longest marine heatwave event in the Black Sea, which lasted 97 days. So we can quickly check that in our visualization here. So let's say I want to look at 2018. So we have 9 marine heatwave events. And if we plot it, we can see that on several occasions here, we indeed exceed the threshold on a lot of very short occasions. And if we look at 2020 here, we can see that
here from the end of September to almost the end of the year. I don't think we go below the threshold here. We indeed have a very long here marine heatwave event at the end of the year 2020. We have some more smaller here. Yes, we have 6 of them in total. We have a very intense one, but short one here. So yes, this is consistent with our findings here. And finally, as a bonus, I can use these lists that I have computed to perform 2 very small plots here, just to see the evolutions of the number of marine heatwave events over the years, and the evolution of the duration of the maximum duration of marine heatwave over the years. And if I do that, I can see that over the years we have more and more frequent marine heatwave events. We can clearly see an increasing trend here from 2000. And quite the same observation here with the maximum duration of the events. So we have a very strong internal variability, but still we can see that, especially since the early 2000s, we can see quite an increasing trend. So we don't have a lot of data points, but we can probably expect that in the future, because of global warming, we'll probably have more frequent and more intense marine heatwave events in the Black Sea. Okay, so I think we can finish this tutorial. So we are reaching the end of this training. So I think you have now plenty of tools to perform manipulations and data analysis over the Copernicus Marine Service data catalog, especially regarding climate change, because we have some tools to perform long-term trend analysis, correlation with variables over very long periods. So yes, I hope you enjoy this training, and I thank you very much for your attention. So if you have any question, feel free to ask.
Thank you very much, Alexandre. We actually got one question on the chat in relation to the solution you just presented. The question is, could we use a loop that takes all the years from the data set without creating the list range 1993 to 23, so that can be extended to other data sets with a different time range?
Yes, I think you could. Basically, instead of writing in the range here the actual years that you need, you can refer to your own data set. So you can, for example, what is my data set? This is this one. I think you can retrieve just the minimum and maximum years that is available in your data set, and write those instead of the values here written as such. I probably can do it live, hopefully. Not too sure if I can do such a thing. Yep. How do you retrieve a year from a datetime 64 variable? Quickly checking. Yes, we can probably do something like this. So yes, I have my minimum. I have my maximum. And then I can just save them in variables. Ah la la. Make sure I convert them to integers. Ah la la, what is happening here? All right, so we are almost there. And yes, I got my results. So basically here, what I've done is to convert the 2 time steps, the maximum minimum, into years. So datetime 64 is a format that starts in 1970. So you have to add it to get the actual year of the data, which is the minimum maximum. And then for any data set, you can perform the analysis on the entire range if you have a different time range than 1993 to 2022. So in my case, I get the same results, but if I had a smaller data set or longer data set, I would probably, the analysis would be on the entire period, depending on the data set. So yes, it is entirely possible.
Okay, thank you very much for suggesting this other solution live. I think we are reaching the end of today's tutorial, so I will just take 2 minutes to give you some final answer about recording and all other elements. So thank you again, Alexandre, for the session today. I hope it was very useful to our participant, and obviously we are very sorry about the technical issues we had at the beginning. And hopefully we could find a solution for that. So I just wanted to let you know that you'll find both of the replays and the polls on the event website through the menu at the top of the page. We will also send you an email to let you know when the replay is available and the link to the poll about today's webinar. So if you could let us know what you thought of this live tutorial demonstration, it would be good. It means we can organize more of these events in the future if this is something that you find useful. And sorry, I just wanted to also let you know about the Copernicus Marine Service YouTube channel, where you'll find a rich library of webinar replays and training sessions from the past few years. They're all freely available, of course. Each video focuses on a specific theme, whether a region of the world, a blue economy sector, a practical example of how ocean data supports real-world applications. So it's a great way to deepen your knowledge at your own pace and explore use cases that match your interest. You can also discover all the Copernicus Marine events, both upcoming and past, via the events tab in the top right menu of the website, where you can open an event page for details and registration. And we will just finish today's session with a short note about the next event we're organizing. It's going to take place on the 3rd of February. And we are going to focus on the My Ocean Pro viewer. This will be a step-by-step live tutorial to show participants how to use the viewer and get data from it. Once again, it will be a hands-on session, so feel free to register if you're interested in this. You'll have the opportunity to manipulate the viewer during the session, and you will be guided by our presenter and a series of practical exercises once again. And please note that places will be limited, so we encourage you to check the event section of the Copernicus Marine Service website in the coming week to secure your spot. So once again, we hope this webinar was useful to you. Thank you for joining. Apologies for the technical issue at the beginning. We will leave you here now. Have a great rest of your day, and goodbye, everyone. Thank you again.